So we're going to start out with a derivation of the addition operation on the representation. And this is how I've set up the derivation. So I've put it inside a module so that it's kept isolated from the rest of the module. And I can do things without name collisions and that kind of thing. And what I've done here is I've defined the syntax for the operator. So it's this plus circle, and it goes from AF to AF to AF, which, as you recall, is pairs of rationals to pairs of rationals to pairs of rationals. And so I know that the left-hand side is going to look like this. I'm going to want a pattern match on the products to get out the components F1 and F2, G1 and G2. But I don't yet know what the right-hand side is, because that's exactly what we're trying to derive here. But what I do want is for this monoid homomorphism property to hold, that the meaning of F circle plus G is extensionally equivalent to the meaning of F plus the meaning of G, where this plus is addition on functions, which we defined earlier. So here is a standard proof form that you see in AGDA, and I've left this hole here where I've said that this is equal to this, but I don't know how yet. So what I'm going to do is I'm going to work forwards and backwards at the same time, and I'm going to meet in the middle. Okay, so let's first work forwards from the meaning of F plus G. Okay, another thing I just want to mention is this is extensional equality, so I have to prove it for an arbitrary x, and that's why we've got this x here and at the end. Okay, so the first thing I'm going to do is just add one of these equivalence operators, and I'm hoping that it will just be equivalent with respect to normalization, and so I won't have to provide a reason inside these angled brackets about why that is equivalent. So what do we know about F and G? We know that F is equivalent to F1, F2. And we know that G is equivalent to G1, G2. So I think we can say that's true. And so now I'm going to save the file and check it. And that has gone through. That's really nice. Okay. I'm not sure at this point that we can go any further in the forward direction. So what we're going to have to do is start working backwards. So what I'll do is I'll place this here, and what I'm going to do is think about what the meaning of F is equivalent to. Well, that's something I actually do know from the definition of the meaning function. So it's actually lambda x f sub 1 times x plus f sub 2. I know that's true. All right. And then I also know that the meaning of G is something similar. Okay, so that's great. And I can now write function addition here. I can put the whole thing in brackets and then put an x afterwards. But perhaps that's, I haven't done enough there. So what I'm going to do is just simplify that a bit more, because I know AGDA is smart enough to do this. So I'm just going to pretend that I did actually apply function addition to x. I'm just using my knowledge of the function addition definition to do this. Okay, hopefully I haven't gone too far for people who are observing this. And if I check that, that holds as well, which is really nice. Okay, so now I'm looking at something, and I know that I want to go backwards until I've got some constant times x plus some other constant. And I don't have that at the moment. I've got 2 times x's here. I've got one here, and I've also got one here. So I just want to have one occurrence of times x. And so what I'm actually going to need to do is like rearrange this equation. Sorry, it's not an equation. I need to rearrange this expression. So the first thing I'm going to do is I'm going to rearrange the brackets on it. I'm just going to use the associativity law here. So I am going to go f1 times x plus f2 plus g1 times x plus g2. I sort of know where I'm going, and you'll see as time goes on. So what law am I going to use here? Obviously the associativity law. And there's going to be a few holes there. It requires 3 holes to be filled. But I can already tell that I'm actually using the symmetric version of it, because this one here is associated to the right, whereas I know the Assoc law associates to the left on the left-hand side of the equivalence. So I know it's going to be something of that form. Okay, so that didn't type check. I've got a parse error of some description. I think I might have one too many brackets. Okay, so that's better. And now I need to fill in these holes, and I know that the 3 things which I'm performing the associativity transformation are f sub 1 star x, that's the first one, f2, and g sub 1 star x plus g sub 2. Okay, so check that whole thing again. That's worked really nicely. Okay, great. So the next thing I want to do, I don't know what's going to go here just yet. Next thing I want to do is do some more shuffling around of brackets, I think. Yes, okay, so I'm going to put this in here, and what I'm going to do is I'm going to reassociate so that we've got this. I'll need another start bracket there. Okay, so that should at least parse. And now I want to use associativity on this part here to turn it into this. That's going to be a forward use of associativity, but I'm going to have to use the Kong rule here. So on something of the form f star 1 star x plus, I want to then use the plus Assoc rule. So we'll refine that, and that's worked really nicely. And the thing I want to do it on is f2 g sub 1 star x and g sub 2. Okay, let's check that again. So those two are equivalent. Okay, now this is really good. Now I think I want to apply commutativity. So I'm going to take this, and I actually want to swap this bit to the front, like that. I just realized I can actually take these brackets off here. So I'm going to do that. I'm going to take these brackets off here because that's the default associativity. I'll put a hole here. Okay, that's very nice, and that's still checked. That's really nice. So what I want to do is apply commutativity just to this bit here. So again, I need to use the Kong rule, and that's going to look like this. So it's going to be f sub 1 star x plus, and then it's going to be brackets square plus g2, I think. Yes, that should be right. All right, I'll just refine that. And then I want to apply commutativity. Now, is that in the forward or reverse? It doesn't matter. That's commutativity, goes both ways. All right, so the two things I wish to perform the commutativity are G1 star x f sub 2. I noticed some yellow appearing there. Okay, that's type checked. That is correct. All right, you can see that I'm slowly massaging this into a form where hopefully I'll be able to use the distributive law. So the next thing is I need to apply associativity once more. So I'm going to grab this, put that over there. And I want to get something like that. There's actually 3 uses of plus there. So is this valid? I think I'm going to have to reassociate. I don't think I can do that in one step, so I think I'm going to have to reassociate within this to that, which is quite different. Cool. So f star 1 star x plus square plus plus square. Great. And then we'll apply plus a sock like that. Let's see how we go. Okay, and the 3 things that I'm applying the associativity to are, in fact, it's going to be in the reverse direction, so I'm going to need to put sim here. Just recheck that, get the goals going. And it's going to be g sub 1 star x, f2, and g2. Lovely. Okay, so the next thing we want to do is another reassociation, so that we've got things in the form required to apply a distributivity law. So I want to do this. That's what I want to reassociate to. So I think in this case, I can actually just apply plus a sock. And the first thing I'll be doing it on is f1 star x. Next one is g sub 1 star x. And the final thing is f sub 2 plus g sub 2. Beautiful. All right. So now what we want to do is apply a distributivity law. I don't know what this is going to be just yet. So I'll copy this up here. And what I want to get to is this. Now that to me is right distributivity of x over f1 plus g1. So and unfortunately it's only on part of the expression, so we're going to need to use Cong again. So that's that. And then in here, we're going to want to apply star distrib r for right distributivity over plus. The variable is x. The first thing in the addition is f1, and the second thing in the addition is g1. It's worth looking up the definitions of these things in the Agda Standard Library so that you know what to fill it in with. Let's see if that type checks. Oh, that type checked the first time. Okay, so that's really nice. Well, now we have something which I know is in the form that is sort of the right-hand side of the meaning function. So I can quite confidently just say this is going to be definitionally equivalent with regards to normalization. And I can say that this is the meaning of F1 plus G1 paired with F2 plus G2 applied to X. Okay, let's see if that works. So that's beautiful. That actually has, that does fit with that. Now you can see that the form of this and that is really similar. So if I were to remove this here and then say, oh, we're complete now, then you'll discover that it goes yellow, which means that there's unsolved constraints. And that's because we haven't yet filled in this definition. So now we need to actually fill in the definition. But we're just going to fill it in with what we derived it to be, which is going to be F1 plus G1, F2 plus G2. And now we can check that that whole proof goes through. And see, that's really beautiful. We found the definition, and now we have the proof that it also satisfies this monoid homomorphism property.